One of the big ways to use derivatives is to find max and min points, because you can see for most turning points at the top there, we get that slope of 0. So where the derivative 0, uh, so that kind of max the derivative 0. So derivative is definitely going to help us. If we can find where the derivative 0, we might be able to find those max and min points. So what we're going to do this afternoon is look specifically at finding the absolute max and the absolute min of a function between two x values. So on some interval, where's the biggest and where's the smallest point. So I've got 4 different kind of sketches here, and we'll talk about basically where these points are and what's special about those points. And then we'll come up with some steps that we could find for sure what the max is and for sure what the min is. So again, on this one, that's definitely the max. And I've kind of given away the special thing here. That point's special because the derivative is 0 there. That's one way we could identify that point. On this picture, where's the min between A and B? Right, so if I'm only considering the points, so it's definitely one of those. To my eye, A looks a bit lower than B, just where it's what I've been trying to draw. So that would be our min. And what's special about that point it's at the end of the interval. So there's 2 possibilities for what type of point the max could be. The max could be where the derivative 0. The max or min could be at one of the 2 ends of the interval that we're looking at. If I look at this picture here, where's my max and min? Yep. And then the min down here at B, right? So here the max and min on that interval are the endpoints of the interval. And we have some spots where the derivative is 0 there, but they just happen to not be the absolute max and the absolute min, which is kind of what we're going to be interested in today, is just finding the absolute. They're local mins and local maxes, but they just happen to lose to the endpoint. Okay. What's going on here? Where's my max and where's my min? Yep. And then, yeah. So what's special about those points? What's going on there, mathematically speaking? So we might call this a discontinuity. And what about the top of the V up here? It goes from increasing to decreasing. What's happening with the slope at that point? Does anyone know? So I totally see why you think that this has a slope of 0, because you'd think like, well, the tangent, I could draw a horizontal tangent there. But like kind of that also looks like a tangent. And that's not flat. And that kind of also looks like a tangent, right? So The derivative there is not 0. Does anyone... It is a spider. Does anyone know what the derivative is there if it's not 0? It's a bit of a tricky one. Nope. Nope. Nice. So here, the derivative does not exist at that point. Okay? Because if you think about the limit as h goes to 0, right? There's my f at a. When h is negative, that limit's going to look positive. It's going to look like that positive slope. When h is positive and you're doing sort of the slopes of the secants on the other side, that slope's going to look negative, right? So you're getting different slopes on either side of that point as h approaches 0. And if you get different answers on either side, then that derivative does not exist. Does that make sense? And that kind of point, it's got a name. It's called a corner point, a sharp corner. So that would be anything that sharply goes from one to the other instead of a nice smooth from one to the other. So that's derivative equals 0. This is derivative not existing. And so what I'm trying to do here is I'm trying to gather up all the possibilities for a max or a min. So we have endpoints could be there, where the derivative is 0 could be there. Here, where the derivative doesn't exist, that might mean that there's a sharp corner that's a max or a min. So that's possible. This discontinuity, if the function's discontinuous, it automatically means that the derivative's not going to exist. Your f at x plus h minus f at x over h. You're going to get some funky values. When h is positive, you're jumping and making secants way up here. When h is negative, you're making secants over here. So your derivative doesn't exist at that discontinuity as well. So instead of thinking discontinuity, I'm going to just bundle that up with derivative not existing as one of the options. Any questions about this picture? And here's my last picture. It's a fun one. So here's my min, and it again is an endpoint. Here's my max, so it's sort of curving up and then quickly turning around and curving back. So that's different than the sharp corner because these are like straight lines and these are curves that come to a weird point. So if it's straight lines, it's called a corner. If it's curved, it's called a cusp point. And same kind of question, what's happening with the derivative there? Like, as long as there's a curve involved, I would call it a cusp. But what's going on with that point there? What's going on with the derivative there? Yeah, there's not going to be one for the same kind of reason. Well, one, the slopes look very different on either side, so the limit as h goes to 0 is going to be different on either sides. In fact, what's happening is the slope is actually approaching infinity. It's kind of going vertical there. You're getting kind of like a vertical tangent in the middle there, and then it's coming off that vertical tangent like that. So your slope is kind of approaching positive infinity on one side, and then negative starts off at negative infinity on the other side. So definitely the derivative is going off to infinity. We're going to say that the derivative, it doesn't exist there. And these are kind of, my claim is these are all the options for a max or a min. if you have a max and min between two values, it's either going to be an endpoint, a nice turning point where the derivative is 0, or if there's something funky going on, the derivative is not going to exist at that point. Okay, so what we're going to do is we're going to define all of these points as critical points. So a point on the graph is called a critical point of the function if the following is true. If f, the derivative at that point, is 0, if that point is an endpoint, or if the derivative does not exist at that point. And our idea here is all max/mins must be critical points, but not all critical points are necessarily the max or the min. So, for instance, these would be considered critical points, but they don't fit. So where these turning points that were kind of in the middle, they're not the absolute max or min, they are still critical points. If you have something like a cubic shape where it flattens out in the middle and you get this derivative of 0 in the middle, that's still a critical point, but it's not necessarily a max or a min. The derivative is still 0 there, but it's not a max or min. But if you are a max and min, then you definitely are one of these three things. You definitely are a critical point. Does that make sense? Any questions about any of that? And then people always kind of get worried about this derivative not existing. And I'll tell you, 99.9% of the functions we deal with will be either derivative 0 or derivative or the ends of our intervals. Okay, these weird sort of options, a cusp point. I don't know if you've ever even seen a graph with a cusp point yet, or like these weird like branch functions that jump around and change from one thing to the other. Those don't come up very often, so it's just something we kind of have to keep in mind. And so our method for finding the max and min of a function on an interval is going to be this. We're going to find all the x values that are critical points. We're going to find all the points that might be max or mins. So all the points where the derivative 0, both of the endpoints of our interval, and any points where the derivative doesn't exist. We're going to list them all out. We know that the max and min have to be one of these points. So we'll plug in all those values. We'll get the y values. Whichever one's the biggest, that's our max. Whichever one of those is the smallest, that's our min. So we're just going to try that. We're going to try it 3 times in a row. I've written all the questions at the start and then just given some blank space. They're not all going to fit on this page if you've got it printed out, so have a spare piece of paper handy. So for the first one, just interpreting the question, we're going to find the max and min values of this cubic, and then on the interval x from -10 to 8. Have you seen this type of interval notation with the brackets before? Is that something Marshallin does? That went exactly as how I would expect it. But this translates to the exact same as this. just x is between -10 and 8. If it's a square bracket, the endpoint's included. If it's a round bracket, that would mean that the 8 is not included, or the 10, like this interval, is the same as this with just no equal signs. And you can kind of mix and match. One square and one round would look like that. But for us, when we're doing this type of question, the endpoints are always going to be considered because we want to find that absolute max, and that absolute max might be at the endpoint. Okay, so for that first one, we have our function up here. I usually keep a spot somewhere on my page where I'm keeping track of my critical values. And just looking at that question, I already know some critical values. So can you look at that question and tell me some critical values? X equals -10, x equals 8. The two endpoints are critical values. So those are potentially where the max and min are. So later on, we're going to have to test and see, is that the max or min? We're going to have to plug these into the function at the end. And because they're my endpoints, I kind of write them spread out like that, because every other critical value that I find needs to be between there and there. In a second, when we have our derivative, if we find the derivative is 0 at x equals 14, that's nice, but it's not part of this question, so I wouldn't write x equals 14. So I kind of spread them out so that I know everything, remind myself everything should fit between there and there. Alrighty, so let's take the derivative. And we've got our new fancy rule, so we should be able to do this derivative no problem at all. You're like, Mr. Clement, why'd you put those gross fractions in there? That's weird. This is just a trick I like to use to get the derivative that I want. You'll see when the 3 comes down, it's going to cancel out the denominator on the 2/3. 3 times 2/3 is just 2. And then you get x squared. 2 times 9/2 is just going to be 9. And then 1 less power. Minus 35x is just 35. And then derivative of 23 is 0. And to figure out where our critical values are, we look for where this thing's 0 and where this thing doesn't exist. Well, this thing's a quadratic. It exists everywhere. There's no bad x values on this whole function, so that's fine. So all we have to do is figure out where that's 0. So I could jump right to the quadratic formula because all I need is the x values, or I can try and factor this thing. The 2 doesn't factor out, so it would be what I call a crisscross factoring. So 2 things that multiply to the first. It's going to be this. 2 things that multiply to the second. to the last. So -35, 5, and -7. And then my crisscross is -14 and +5. Those do, in fact, make -9. So I got it right first try. So those are my factored brackets. 2x plus 5, x minus 7. And I get x equals 7, and x equals -5/2. As my critical values. They are, in fact, between those 2 endpoints, so they are all potentially that. So now we've taken this function, we found both the endpoints, we found both spots where the derivative happens to be 0, we've decided that the derivative exists anywhere. So this list here of 4 numbers are all my critical values for this function. And so what we've done is we've taken the infinite number of options of x values between -10 and 8, and we've boiled it down to 4. Our max and min has to be one of these 4. Like our max is one of the 4, and our min is one of the 4 options. So all we have to do is pull out our calculators and plug in those 4 values into our original function. original function is 2/3 x cubed plus 9/2 minus 9/2 minus 35x, and then plus 23, I think it is. So can I get some volunteers to pick some of those numbers, pull out your calculator, fire them through, and give me some answers? So everyone pick one and let me know if you got one. Because as I said, I don't have a calculator here. No, it's good. Decimals are good for this. Okay. Okay. Looks like it would round to that, so instead of rounding to 72, go with that. All right, thank you for that. And that was good because we got all four numbers and everyone, nobody mispunched anything in because I've got it up on Desmos here. So we got all the right answers. So that's nice. So what do I do with this information now? How do I answer my problem? So that one's my min, this one's my max. So I can say, therefore, the minimum point is this, and the max point is, we'll go with that. Any questions about this first example? Here, I'll just bring up the Desmos plot so we can see that we got the right answer. So our min, yeah, that endpoint is way down there at -10. It's way down there. It's way lower than the rest of the graph. So there's our min. Here's our max at -2.5. 7 was a potential, or sorry, 7 was the min. Yeah? Did we have that right or did we have that wrong? Oh, I circled the wrong. Oh no, 7 was a potential min. That's right, because the other endpoint was the min. Duh. Okay, sorry. 7 was a potential minimum. You know, if the interval was different, if the interval started at 5, sorry, at -5, You know, if that was our interval, then 7 would be the min. That's what I was trying to say, but didn't say at all. But it turned out that the endpoint just sort of beat that turning point, and then this might have been a max, but it wasn't. So that's the idea there. Any questions about that? Okay, so I got 2 more examples. So now we can try b, which is x plus 4 over x. And our interval is 1 to 3. 4 over x. 4 over 2 would be silly. Okay. So how am I going to start this one out? Yep. So we have 1 and 3 as our 2 endpoints. And then to get the rest, we're going to have to take the derivative. So with this function here, what do I have to do to get the derivative of this function? So rewrite it so that it looks like an exponent. And then we can use our rule from this morning. The derivative is going to be derivative of x is just 1. And the derivative of this, the negative comes down, it becomes negative 4x to the minus 2. And we're going to first solve where this is 0. So maybe I'll move that term over and then just multiply the x squared up. I get that. And then remember, when you square root, you get 2 answers, so we get plus or minus 2. And so there we go, 2 more critical values. We good with that? Mm-hmm. Absolutely not. So that was a trick question. So yes, we're going to keep the 2. That's good. Negative 2, not on our domain. Okay, so just x equals 2 is good. X equals minus 2 is off the interval. And then is that all of our critical values for this function? Is that all the numbers I should think about for this function? The fact that I've asked... Yep, go ahead. Right, so this thing here, does it ever not exist? Are there any x values we can't plug into that? Zero, right? But again, 0 is not in our domain, so that's the point where the derivative does not exist. It's outside of our domain, so we don't have to consider it. Outside of our interval, so we don't have to consider it, but we should be careful. If that happened to be on our interval, that is a point that we would want to consider. And thank goodness it's outside of our interval, because it would be a vertical asymptote there. The function was going off to infinity at 0. So if we're trying to find the max around a vertical asymptote, we wouldn't be able to do that necessarily. So good thing it's off our domain. All right, so we have boiled it down. These are now, in fact, our 3 values that we need to plug in. And it was, so this is going to be 1 plus 4 over 1, which is 5. This is going to be 2 plus 4 over 2, which is 4. And this is going to be 3 plus 4 over 3, which is 13 over 3, which is 4.3 repeating, I think. Okay, so now our conclusion. Max 1.5 and the min is thank you. And we can just double check that. X plus 4 over x between 1 and 3. So this is the only interval we care about. We see x equals 0 is in fact that vertical asymptote, so good thing that is outside of our domain. 1, 3, and 2. So there's our min. It is kind of, that is a flat turning point at the bottom there. And then the other point we found was actually this maximum over here. It looks like local max there as it curves down and away again. Looks like an oblique asymptote going on in there, perhaps. Okay. But again, we only had to consider those 3 dots in this section of the graph that I can't zoom in on because my fingers are too big. Any questions on this example? Oh, I found my work from this morning. Ooh, the last one is fun. I think that's it. Is it a minus or a plus? It's a minus, and it's from -1 to 0.5. All right, so we're ready to move along onto this one. Our last one for today. So I've written down my 2 endpoints so that I don't forget those. Now, how would I deal with these cubed roots to get my derivative? Right, so you're just kind of turning the roots into exponents. So the 5 inside's the numerator, the third root is the denominator. So however you think about that, but I would go right from there to there. And now I have exponents that I can do that rule from this morning with. 5 over 3 x to the, what would the new exponent be on this one? Nice. So subtracting 1 means you're subtracting 3 over 3. And then minus the 2/3 is going to come in front. And what's the new exponent on this one? Thank you. All right. And so I'm going to rewrite it. Maybe I'll write it this way. So I just put the x to the 2/3 on top because it's positive. I put the x to the 1/3 on the bottom because it's a negative exponent. And at this point, I'll pause. Do we get any more critical values here? Zero is 1 because it makes the derivative not exist. Because there is now an x in the denominator, x can't be 0 in the derivative. Does 0 exist on the original function? Can I plug 0 into the original? So this would turn into 0 to the 5 is 0. The cubed root is 0. Can you do the cubed root of 0? Yeah, it's 0, right? So you can plug 0 into this function, and you get 0. So this graph has a point. It's the point 0, 0. It's at the origin. But that point doesn't have a slope. The derivative doesn't exist there. I can't plug 0 into the derivative, but I can into the function. So this is one of these funky examples from my drawings at the front, where there is a point there, but that point has a derivative that does not exist. So we'll look at what this looks like, but this is one of the weird examples, and it happens because I've got a power between 0 and 1. When you do that, x is in the numerator in the original, but when you subtract 1 from that power, x drops down to the denominator, and you get a point where the derivative doesn't exist. Okay, so if I want to do something, so that's where the derivative doesn't exist. If I want to find where this function's 0, anyone got an idea of what algebra I can do? I know it looks scary because we've got those fractional exponents, but I've purposely written it as two fractions. So when you see two fractions with a minus sign between them, what do you start to think? Right, so this one's got a 3, this one's got a 3, this one's got an x to the 1/3, so maybe I'll multiply top and bottom of this one by x to the 1/3. And you'll see that I'm not too mean, because what does that turn this first term into? That's right, that's 5x, right? Because the 5 is just 5, and then x to the 2/3 times x to the 1/3, you add your exponent. And then the back is just minus 2. So we're multiplying here, not adding, so that does stay as a 5. All right, so now we're solving where 0 is. Now that we've captured, we haven't forgotten about this denominator, we can kind of forget about the denominator. If this fraction is going to be 0, it means that the top is going to be 0, which means x is going to be 2/5. And 2/5 is 0.4. It fits in just before the end of the interval. and we're ready to plug in our critical values. So f at -1 is the cubed root of -1 to the power of 5 minus the cubed root of -1 squared. -1 to the power of 5 is -1 still. The cubed root of -1 is -1. -1 squared is +1. The cubed root of +1 is 1. And I get -2 there. F at 0 is in fact 0. We talked about that. If you do the cubed root of 0, you get 0. Oh, and here's where the wheels fall off the bus for me. Can someone punch this one in for me? So 0.4 to the 5, and then the cubed root of that, and then take away 0.4 squared to the cubed root of that. And I'll need someone to do the 0.5 as well. Is that 0.4? Okay, thank you. .315. Looks like those are awfully close, but it looks like, oh, it doesn't matter because we've got the -2 there, so it really doesn't matter which one wins between there. So okay. So our max is the origin, and our min looks like it's at -1 and -2. And hey, what did we just find? There we go. There's your first cusp point. If you've never seen one before, they're not too scary. I mean, the fractions weren't particularly nice to deal with, but that's sort of what happens is you get that x that drops into the denominator when you take the derivative, so you can't plug in a value for x, but you can plug that number into the original. That kind of is what happens when you get these cusp points there. And then I think 0.4 was a local min, which is good, but -1 was even lower, so it won. Okay, -1, -2. So that example there was just to show you an example of a critical point that is the derivative not existing. We won't do too much of that. And so they can look like that. If I change that to a plus, it just flips it over. I forget how to make just a vertical tangent. Oh, it would be something like this. Yeah. So it can also look like that, where it doesn't, it's not a max, but the derivative doesn't exist there because it's going vertically through that point. So that's another example. The 3/5, when you take the derivative, there'd be a -2/5 in the derivative as an x power, and you can plug in 0 to that. So that's just another thing it might look like, but it would be considered a critical value, and it might be a max or min. Any questions about this crazy example? If a fraction's 0, if I'm actually just solving where it's 0, then if the fraction's 0, then just the numerator is 0, not the denominator. If the denominator is 0. So where the denominator is 0 is a critical point, but it's a different type. It's where the derivative doesn't exist. So you do have to consider both. Any other questions?